Now we're going to consider damped harmonic motion. We talked about this very briefly at the beginning of the previous video. If I have a spring with a weight at the end of it, this is just one example, I can pull that spring down or push it up and then release it. And when I do that, let's start by pushing it up this time. It has a starting point above its midline, but when I release it, it drops below its midline. Then it bounces back up, but not as far. It bounces back down, but not as far, and so on. So the curve, if we trace it out over time, that it follows looks something like this. Let's take a look briefly at what the curves either side of this graph look like. In other words, what if I trace all the maximum values and all the minimum values? That begins to look exponential. And in fact, that's exactly what's going on. Without going into too much detail, because the theory behind it is a bit more than we are really ready for in this course, a function that models damped harmonic motion can be written like this. K is a constant that tells us how big the curve gets. It's our amplitude. And then we have an exponential function times either sine or cosine of omega t. We already know about K, and we already know about omega. Those factors do the same things as they did before. K is the amplitude, and omega is the number of cycles that occur between 0 and 2 pi. What's different about this function is this exponential factor. This is the thing that bounds or constrains, graphically anyway, what would normally be a cosine function in the case of what I've got graphed here, to a cosine function that gets shorter and shorter with each cycle. We still talk about a period. It's the length of time it takes to get from a maximum to the next maximum, even though that second maximum isn't as tall as the previous one. And that period is still 2 pi over omega. Some new vocabulary is this thing called the damping constant. The damping constant can be found in the exponential. It's the coefficient of t. So this c value here is what we call the damping constant. It governs how much restriction there is on what would have been a sine or a cosine curve. We also still talk about the amplitude. Now the amplitude changes from one cycle to the next, but the maximum that it ever reaches is this value k here. So we'll still refer to that as amplitude. We also still have frequency, and the formula for that is still omega over 2 pi. So the only new piece here is the damping constant. Let's take a look at an example. All right, here's our problem. A mass is attached to the end of a spring. The mass is pushed up from equilibrium by 30.1 centimeters and released. The damping constant is c equals 1.5, and the period is p equals 3. Find a model for the motion of the mass. Well, we know that we want our equation to take this form. A times e to the negative ct times either sine or cosine of omega t. We have some of this information directly. We know that A is our amplitude. C, kind of hard to see in the formula here, that is my damping constant. And the period is 3, but that's not directly in the formula. I need to use that to find omega. Once I have omega, basically I just need to plug the values in, and I have the equation I was looking for. We know the period, so we're going to use the formula. Period, you could of course use just P for period. Period is equal to 2 pi divided by omega. I know the period, it's 3. I'm looking for omega. So let's multiply both sides by omega and divide both sides by 3. I get 2 pi over 3. That's omega. That's what goes in here. So let's rewrite our equation. A is our amplitude, that's 30.1. E to the negative c is our damping constant, that's given as 1.5, times t, times the sine of omega, which is 2 pi over 3, times t. Now there is an error in what I've just done here. When I wrote this out here, I wrote it with a sine, but it could be a cosine. So the thing to do is to take a look at what's going on with the system here and figure out whether we're actually working with a sine or a cosine. A mass is attached to the end of a spring, and as you begin your experiment, it will be at rest. So we have the spring, the mass resting on the midline here. Imagine that the spring is relaxed, except that it's pulled down slightly by the weight of this the weight of this mass. But once it's allowed to come to equilibrium, there's no movement, it's just sort of sitting there. Now, before you let it go, you're going to pull it down from equilibrium by 30 centimeters. You're going to start by moving it down here. So once you do that, that's actually where the thing is going to start. And then you release it, and it goes up and down and up and down. So what kind of curve does this look like? It looks more like a cosine than a sine. I've not done a very good job drawing it here, but a sine would start here. A cosine would start either up here or down here. So this is a cosine curve. Let's change that in our formula. Cosine of 2 pi over 3 times t. So this can either be a sine or a cosine. In fact, it will frequently be a cosine. If you start with your mass here and pull it down before you release it, or push it up before you release it, then it's starting above or below the midline. Sine graphs start at the midline. An example of a sine curve might be if you let your system start at rest, but give it a push before you start it, before you let it go, or give it a pull just at the minute that you start it, not pulling it and releasing it to start down here, but starting it here and just as you start your stopwatch, pulling it down to let it go, or pushing it up before you let it go. That would result in a sine wave instead of a cosine curve. Now I've just realized that I've been using A here instead of K, which is what I used in the formula on the previous screen. But again, it doesn't really matter what letter gets used here. What matters is the position that it's in. I'm not actually sure why your textbook uses A in the trigonometry, in the analysis part of the textbook, and then switches to K for this application. Maybe it's just that that's how the physicists of the world expect to see their damped harmonic equations. They expect to see a K there, but why they expect to see a K there, I really don't know. What's important is what's in that position. What's in this position is the damping constant, and what's in this position is omega, or what was it, C, I think, when we were doing the analysis earlier in the quarter. So what's in those positions is what is important. Well, that was fairly short and sweet, but that's pretty much all I expect you to take away from this particular topic. Know that there are a lot of different systems that can be modeled using either simple or damped harmonic motion functions, and that they come up a lot in the real world suggests that there are a lot of places where it'll be handy to know how the system behaves, and you can do that by modeling it using an equation. Also know that while it's easier to work with a simple harmonic equation, it's not very likely in the real world that you'll ever run into that. Even if all you have resisting or working against your system is air resistance, that's something that's going to slow down your spring system or whatever it is you're working with until it stops. Sometimes we get a super viscous fluid like oil, and if our spring system is working in oil, then it's going to slow down quite a bit. But that's actually what you want in some circumstances. Think about pistons moving in a car. Now, I'm not a mechanic either, so I'm not actually sure how accurate that analogy is. My point is that the damped harmonic system is the damped harmonic motion model is actually much more realistic. All right, we have one more topic in this section, and that is the definition of phase and phase difference.